In this video, we're going to talk about surface gravity. Planets, stars, moons all have a gravitational field since they all have mass. That field is largest at the object's surface, where the distance from the center of the object is the smallest. In other words, when r is the radius of the object. Only the mass of the planet that's closer to the center of the planet than you are contributes to its gravitational field. So the field actually gets smaller if you were to actually tunnel down below the surface. So for instance, if this is our planet and I tunnel into this region right here, my R actually decreases and that gravitational field will decrease. Determine the surface gravity of the Earth's moon. Its mass is 7.4 times 10 to the 22 kilograms, and its radius is 1.7 times 10 to the 6 meters. Go ahead and pause the video now. Okay, so let's go ahead and check your work and see if you have the correct answer. Hopefully you wrote down that G is equal to capital G, capital M over R squared. Substituting in the numbers, remember that capital G is the universal gravitational constant. It's equal to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. We multiply that by the mass of the moon, which is 7.4 times 10 to the 22 kilograms, divide by the radius squared, which is 1.7 times 10 to the 6 meters, and you should end up with the gravitational field of 1.7 meters per second squared. Compute G for the surface of a planet whose radius is double that of the Earth and whose mass is triple that of the Earth. Go ahead and pause the video now. Oh, keep in mind you will have to look up the radius of the Earth and the mass of the Earth. Okay, so let's take a look at the answer. The gravitational field is G times 3m of the Earth divided by 2r of the Earth squared. There's two ways to do this. One is to actually put in the mass of the Earth and the radius of the Earth. That's what I suggested before we cut off. And the reason I suggested that is because a lot of times students want to have the numbers. I also want you to practice using the numbers. Okay. The other way to do it is this. If I look at what I have here, okay, I'm going to use red. Okay, look at this. I have G, I have M, and I have R squared. And what does that leave me with? 3 over 2 squared times G M over R squared. Well, what's this? This is equal to the G of the Earth. Okay? So then I get 3 divided by 2 squared, which gives me 3/4 G. I know G is equal to, this number right here, is equal to 9.8 meters per second squared. Okay, so substituting in the 9.8 meters per second squared times 3/4, I should end up with 7.32 meters per second squared. Or you could just put in the mass of the Earth, which is approximately 6.4 times 10 to the 24, I think, and the radius of the Earth is 3.6 around there times 10 to the 6. Okay, so plug in your numbers and you can get this. Okay, again, we're going to look at the mass in terms of density and volume, and remember that most planets, actually all planets, by definition, are spherical in size. Keep in mind, though, that the planets actually have some squishing effect, which we call oblateness, due to the spin. So they're not completely spherical, but for this case and for these types of problems, we're going to assume it's actually a sphere. So now what we're going to do is look at surface gravity in terms of the planet's mass, density, and volume. Okay, so Again, we're going to replace mass with density times volume. We're going to assume that the volume is a sphere, which is 4/3 pi r cubed. Substituting that in, notice that the r squared here cancels out with 2 here, and we're then left with 4/3 g pi rho r. Okay, where again, rho is the density, g is the gravitational constant, r is the radius of the planet, and pi is a math constant, 3.14. Okay, compute g for the surface of a planet whose radius is double that of the Earth and whose density is the same as that of the Earth. Go ahead and pause the video now. Okay, so let's take a look at the solution. I'm sorry, the answer. The correct answer is C, 2g. If the radius is doubled, then it's going to be twice as much. Compute g for the surface of a planet whose radius is the same as that of the Earth and whose density is 1/3 of that of the Earth. Go ahead and pause the video now. Okay, so let's take a look at the answer. Hopefully you got B, 1/3 g. The density is directly proportional, as we saw from this equation right here. Directly proportional. Compute g for the surface of a planet whose radius is half that of the Earth and whose density is 3/2 that of the Earth. Okay, if you need more time, go ahead and pause. If not, here's the answer. The correct answer is C, 7.4 newtons per kilogram. In the next video, we'll talk about gravitational fields in space. So this is where we have to have a different radius than that of the surface of the planet.